Thanks for the introduction. Hello everyone, I'm Tony from Peking University. I'm going to introduce our paper, H2-LLM, Hardware-Dataflow Co-exploration for Heterogeneous hybrid bonding-based low-batch LLM inference. In recent years, we have entered the large language model era. A wide range of large language models have emerged, which have become the SOTA solution for many applications, such as chatbot, code generation, and AI-assisted web search. LLMs have been widely applied to edge services to provide local service, protect privacy, and support personalization. Different from cross services, which process tens to hundreds of requests, edge services behave a low-batch nature. For example, the personal chat helper communicates with a single user. The virtual assistant interacts with both the user and several application interfaces. The agent bot responds to multiple customers after querying the knowledge database. LLMs are based on transformer decoder layers, which mainly contains an attention block and an FFN block. The attention block projects the input to QKV vectors and interacts them with self-attention. The FFN block processes the input with two linear layers separated by the activation function. There are several variants of the model architecture. In multi-head attention, each query head is paired with one key-value head. We can share the key-value head among query heads to form attention variants. For FFN, we can add one more linear layer or share the same input with the attention block. LLM inference contains two stages. In the prefill stage, the model processes the prompt in a single step and generates the first output. In the decoding stage, it takes the previous token as input and produces one token at a time, gradually building up the full sequence. Accordingly, the workload can be categorized into prefill or decoding-heavy types. For example, summarization and QA have much longer prompts, leading to longer prefill latency. On the other hand, chatbot and code completion have comparable prompt and output lengths, leading to longer decoding latency. The two stages also behave different properties. The prefill stage is compute-intensive, while the decoding is memory-intensive. To efficiently handle the two stages, existing accelerators adopt centralized processor for prefill and DRAM-based near-memory processing for decoding. Different from the centralized processor, which places the computation logic outside the memory module, AMP architectures place compute logic into the DRAM die. In this way, we can reduce the data access latency and increase the total memory bandwidth. Such a computation paradigm has been commercialized in the industry. For cloud platform, Samsung proposed HBM-P, which places processing engines in HBM's memory dies. ISCA'25 proposed GDDR-P, which places processing units near each memory bank. For edge platform, they also propose conceptual products based on LPDDR memory for low latency inference. Despite the benefits, they face several challenges for edge LLM inference. One of the key challenges is their poor computation capacity. For example, existing commodity designs can provide much higher bandwidth than the memory interface. However, their computation bandwidth ratio only ranges from 1 to 2. This prevents them from fully accelerating low-batch inference. We conduct roofline analysis to demonstrate this issue. Although AMP can outperform centralized processor and the low arithmetic intensity, its poor computation capacity limits the speed up. And the high arithmetic intensity, AMP cannot bring speed up, while the centralized processor is still memory bound, leading to low resource utilization. The low computation power stems from the DRAM technology. It provides much slower transistor speed and fewer metal layers for placement and routing. Besides, to provide enough capacity, it also provides limited area budget. Alternative solutions are expected for better AMP customization. Recently, hybrid bonding has emerged as a next-generation integration technology, which vertically stacks the DRAM die to the logic die. Hybrid bonding has two benefits. First, the massive I/O can provide high bandwidth. Second, we can adopt the logic die to enhance the computation power. However, it is still challenging to architect hybrid bonding accelerators. To balance the cost and performance for edge scenarios, less advanced technology node is a practical choice. Since the massive I/O is driven by numerous controllers, they will incur high area overhead. For example, in an industry product, hybrid bonding controllers take up nearly 40% of the logic die's area. According to our further analysis, although reducing the bandwidth can save more area, the poor bandwidth will limit the computation utilization. Therefore, we need to balance the computation bandwidth trade-off inherent in hybrid bonding technology. Besides, existing data flow designs cannot fully utilize the resources. Most proposals adopt fixed operator mapping. For cloud inference, since different operators have huge variation, it is feasible to adopt fixed mapping. However, as analyzed before, edge inference has more complex choices, and fixed mapping cannot fully utilize the resources. On the other hand, existing mapping exploration constrains the operator placement. Such a constraint shrinks the external bandwidth, which can hurt the prefill performance given the high computation bandwidth ratio of edge accelerators. A practical solution is to conduct operator fission, which splits the operator to both channels. However, existing design only conducts fission to fixed operators under fixed partition. Therefore, we need to design more flexible mapping to fully accelerate both prefill and decoding. To tackle these challenges, we propose a hardware and data flow co-exploration solution. We first propose a generalized architecture template for hybrid bonding-based low-batch LLM inference. Based on the template, we then propose a generalized data-centric data flow abstraction to fully unveil hardware performance. Finally, we propose a design space exploration framework to guide architecture and data flow selection. H2-LLM adopts the heterogeneous architecture, which contains a centralized processor for compute-intensive operators and an NMP-enabled memory system for memory-intensive operators. Due to the cost considerations, the memory system may contain both normal and NMP channels. The hybrid bonding channel contains a memory die and a logic die. Each DRAM bank equips distinct I/O to provide abundant bandwidth. The external interface on the logic die is used for normal access and instruction transfer. The input global buffer is shared among PEs to avoid data duplication, while each PE has distinct weight and output buffers for independent computation. It takes 2 steps to conduct NP computation. The first step is to partition operators among NP channels. During partition, we skip the batch size to avoid weight or KV cache duplication. Splitting the input hidden DIM incurs partial sum reduction across different channels, while splitting the output hidden DIM incurs input duplication. The jointly affects the pre- and post-processing overheads. To minimize the overhead, we adopt a performance model to find the optimal factor. This function has an analytical solution, which will be used to guide the tiling factor selection. The second step is to conduct intra-channel operator execution. Given the tile assignment, the input is evenly scattered to each bank, which will be collected by the global buffer. The weight and output tiles are split along the output hidden DIM, so that each PE can produce distinct results. The execution involves 4 steps. The input tile is first collected by the global buffer. Then, all PEs load weight tiles in parallel and conduct computation locally. The memory access and computation can be overlapped using the double buffer technique. After the full output tile is produced, it will be stored back to a DRAM, and the execution finishes. Given the architecture template, the data-centric data flow abstraction can be used to explore the optimal mapping. The key insight is that existing mapping is constrained by directly assigning the computation engine. Therefore, we first bind memory channels to each operator before assigning the computation engine. The channel binding procedure contains 3 steps. The first step is to partition the operator graph into subgroups according to the topological order. For example, given the parallel transformers operator graph, we can partition it into memory access groups as follows, and each memory access group occupies all channels for further allocation. The second step is to conduct coarse-grained binding to each memory access group. We first extract each memory access group's weakly connected components, which are named as memory partition groups. For example, The first memory access group can be decomposed into 3 memory partition groups. Then, we will assign separate channels to each memory partition group, which can be described by the group channel mapping. In the example, the channel set can be partitioned as follows, and the GC map can be generated accordingly. The last step is to conduct fine-grained binding to determine each operator's channel allocation. For each memory partition group, we first stratify it according to the dependency. For example, the MPG P00 can be split into 2 operator tiers. Each tier occupies all channels assigned to the MPG, since they will be executed sequentially. Since operators in each tier can be executed in parallel, we further conduct operator channel mapping in each tier. In the example, we can split channels as follows and generate OC maps accordingly. The transformer layer execution flow can be organized as follows. Operators in the prefill stage are executed sequentially on the centralized processor. For decoding operators, given the full operator channel binding, we can organize the execution flow hierarchically. First, all memory access groups are executed sequentially. Second, memory partition groups in each memory access group are executed in parallel. Third, operator tiers in each memory partition group are executed sequentially. Finally, each operator is executed on the centralized processor or MP channels or conduct fission on the 2 accelerators. To avoid interference, the fission is conducted along different attention heads or the output hidden dim. Finally, we propose a DSE framework to find out the best design. It contains a model parser and an exploration engine, and takes the workload information, architecture parameters, and DSE settings as inputs. The exploration is conducted as follows. First, the population generator randomly samples the initial population. Then, the population passes through the capacity checker, which filters out-of-memory designs. The legal designs are then evaluated, and the top case selector passes the candidate individuals to the population generator, which adopts genetic algorithm to sample the next population. After multiple turns of exploration, the framework reports the best architecture and data flow design. To evaluate the performance, we adopt tile flow and remulator for simulation. The centralized processor is a TPU-like processor, and we construct the design space according to a real hybrid bonding design. We choose fixed parameters when comparing with baselines. For benchmark configuration, we select 4 datasets with both prefill and decoding-heavy properties, and choose 3 models covering all layer variants discussed before. We compare with 3 baselines: centralized processor only, Samsung's LPDDR in products, and SK Hynix AIM design, which reports the highest in-die AMP computation capacity. Our evaluation shows that H2-LLM can perform both the centralized processor and existing AMP designs. We then compare our data flow abstraction with existing fixed mappings and existing exploration. Across all benchmarks, our exploration can outperform best fixed mapping and existing exploration, proving its capability. Finally, we conduct exploration analysis on different dimensions in the architecture design space. We first analyze the computation bandwidth trade-off by evaluating the performance under all legal combinations. We can find that under the lowest bandwidth, increasing the computation capacity brings little gains. The insufficient bandwidth prevents the full utilization of computation capacity. On the other hand, although the design with the highest bandwidth is good for single batch inference, it behaves poor under highly concurrent scenarios. To keep performant across all scenarios, it is necessary to select a moderate computation and bandwidth combination. We then analyze the effect of SRAM buffer size. We can find that increasing the input and output buffer sizes brings improvement under large batch sizes. This is because the data volume increases along with the batch size. A larger buffer size can avoid repeatedly transferring huge tiles. On the other hand, increasing the weight buffer size is beneficial to small batches. This is because weight access overlap becomes poor, and transferring larger weight tiles can improve the bandwidth utilization. Finally, we analyze the effect of the MP resource distribution. We can find that increased MP channel number from 2 to 4 can bring performance improvement. This is because increasing MP memory capacity enables us to assign more operators. However, Further increasing the channel number brings little speed up. This is because under fixed resource budgets, excessive channel allocation leads to WIMP per channel computation capacity, which hinders the performance improvement. To summarize, in this work, our aim is to architect hybrid bonding-based Edge-LLM accelerator with the awareness of technology properties. To this end, we first propose a general architecture template. Based on the template, we propose the data-centric data flow abstraction. Finally, we conduct experiments to prove H2-LLM's better performance and provide several takeaways for future design. That's all of my presentation. Thanks for your listening. The code has been open source, and welcome to reach out for further discussion. Thank you.